Okay, happy Friday. We're just going to build some things today. You're going to take short videos, show me that you built them, and I'll check you off. All right? So, um, remember, a circuit, it has current, it has voltage, and it has some resistance. Current, just think like water, that kind of current. Voltage is the pressure moving that water. Resistance decreases voltage. So we've also, something really important to understand, for you to be shocked, for you to get energy to make something, it requires that you create power. And that's current and voltage. If you just have current, it's not going to move through this line. If you just have voltage, there's no water to move through the line. So it takes both. Sometimes you hear people say, it's got this much voltage, as if it's got a lot of power. Well, it doesn't until you know that. All right. Please build a project with as you press the switch. We went through and did each one of those. And what we realized pretty quick, on a lamp anyways, that it does not produce, as you go through it, we discovered that lamp doesn't really matter the direction of current or polarity. And we hopefully checked, and we also did this to the motor. We realized when you change the polarity on the motor, it reverses direction. It go one direction, change the polarity, change plus and minus. It goes in the other opposite direction. It can start to have, depending on the lamp or motor, it can draw more current. That's one thing about current. Voltage and current and voltage and resistance we set with components, the draw is depending on how much energy. It will always try to draw as much energy as you'll let it, that it wants. If it draws too much, you burn a fuse. And that's why if you pull too much current through your house, you'll flip a switch and the power goes off. You have to refill the switch. We did an LED. This is super sensitive to polarity. If the lamp was none, the motor was changing direction. LED, if you do it wrong, it won't turn on. The upside on this LED was that it uses very little electricity. And then we talked about that. Resistance. All right. What am I doing here? All right. And what we did is here. Let's go back here a second. I'm sorry. Okay. So as we increase resistance, if we switch these out, for example, to each one, R2, R3, R5, this LED light kept going down. You know, and so there's more resistance, less voltage. All right. And then we built one motor and see what how fast this fan spent. And then we put two motors in there and it really sped. So we increased voltage by increasing the batteries. All right. So you can say voltage batteries in series, when they got positive, negative, connected over positive, negative. So it's positive to negative. We call that voltage in series, and the voltage adds up. So if this is 3 volts here, 3 volts there, 6. So voltage totals V1 equals V1, V2. If they're connected in parallel, here's one, same positive, positive. So it's positive, positive, negative, negative. Does it spin really that much difference? Not really. But what it does is it ends up being, as we isolate each one of these circuits, is the voltage ends up being equal. So voltages are equal when they're in parallel. All right. Next, we built this circuit with an LED resistor. And then we put the resistors in series. And then what is resistance to the circuit? Well, it actually adds up. So just like voltage adds up in series, so do resistance. So resistance total equals R1 plus R2. Then, when they're parallel, as in this case, the resistance actually goes down. So when you put two resistors in there, and several people didn't quite understand this, so I wanted to make sure, and so I'm going through it again, that the resistance actually goes down. Same two resistors, but we put them in parallel. So these both resistors share the same positive, share the same negative. And the way to think of this is, and when they're this way, there's still just one tube going to the LED, and you keep putting more and more resistance in there. This one has two tubes. So if we use that water analogy, there's two places for the water to get in. The one with the higher resistance is going to let in less water, but it's still going to let it in. The one with lower resistance, is going to let in more water. So you got two places, quote unquote, the water moving through. If the LED is brighter or lighter than when the resistors were in parallel, is the LED brighter or lighter than when the resistors were in parallel? And it's brighter, and so R total equals 1 over R plus 1 over R2. And that's just a fancy way of saying is the resistance is going to go down as you increase the number of resistors. As we do this, it goes down when their lines set up in parallel. The LEDs are brighter when which of the following is true. The LEDs are brighter when we increase voltage, when we decrease resistance. They're both true. And that goes to Ohm's law. And remember, volts are E in this case. But you can kind of see, and we also remember, there's the power curve. And I think that's really important to keep remember what those are. We won't quite, with this class, we won't, but down the road, we're going to get into that. If you could keep pursuing some engineering, especially electrical engineering. But we can calculate voltage by dividing current by resistance. We can calculate current by dividing voltage by resistance. We can calculate resistance by dividing voltage by current. And so these are all ways of remembering that. Just drawing out a triangle and remembering. All right? So today, I want you building again, and we're going to build a digital logic OR circuit. And this is, if I press either one of these switches, the LED goes on. It lights up. This is called an OR circuit. See why it's OR? Because either one will work. Go ahead and build it. Videotape it. Just take a quick, and the videotape just do 2 seconds showing it works. All right? An AND circuit, and that click is because that's where they want to put content there, sorry. If you slide, this one requires both. So in an AND circuit, go ahead and build this, and I want you to think about what's going on there. What needs to happen for this LED to light up? This is called an AND circuit. This switch and this switch results in an LED. Again, take a video. So that's an AND circuit. But we also have logic. We're going to use this. So in the first one, if either one of those are true, let's go back. There it is. So let's go back in this drawing. If either one of these are true, light up the LED. This is not. This is the opposite of an OR. This is a NOR circuit. So this one turns on. Look at this. Go ahead, click it, and then try these. Watch what it does. Well, 1, 2, 3. Hopefully you built this. Take a quick video of this. I want at least 5 videos today. All right, so there's the NOR circuit. It does the opposite of the OR circuit. And then you have it, not surprisingly, NAND. Now these 2 little blue ones right here, they go underneath this, so the whole thing's level. So this is the opposite of a NAND circuit. And you can kind of see it's same kind of idea. There's the LED, there's a resistor in between it. All right? So, that's what we call an opposite of a NAND, opposite of that. We use OR, AND, NOR, and NAND circuits are the basic. Now they become transistors. They don't use LEDs, switches, physical switches. We use what are called transistors. And hopefully in a computer science or electrical engineering class we'll talk about what transistors are, but it's basically a little circuit, a little switch like this. These little switches and NAND or NOR are what we use to control computers. So make sure, I want to see a picture of an AND circuit. Then the last thing I want you to make is go to the experiment book, green book you've got, it looks green to me. It's 102 to 305. Pick one from there. Just have fun. Pick something you find interesting. Take a few minutes. Challenge you, make something a little complicated. And then send me a video. All right. I hope you have a great Friday. Hope you have a nice weekend. Hope the weather's good. It's supposed to be nice. Take care, all.